today I want to talk about twisted bilayer graphene and the properties of it. First, let's talk about single layer graphene. It's a brief introduction of it. So first, it's a 2D material formed with carbon atoms, which means it just has a single layer of atoms and nothing on the z-axis, only on the x and y plane. And the lattice structure of it is hexagonal lattice, and you can also say it's a honeycomb structure. Uh, Also about single layer graphene, it has high efficiency of conducting heat and electricity, uh, but it has a property of a semiconductor. Uh, People are considering using it as a next generation electronic devices material. Also, it has it can be warped into a carbon nanotube, and it has which the carbon nanotube is. It has strong material per unit mass in comparison with steel, and this is the Bernal or AB stacked graphene. It has two layers of graphene. Uh, you can see that the black line and red dot, they form like they represent one layer of graphene, and the blue dot and gray lines, they form another layer of graphene. Notice that like each lattice circles one atom from the other layer at its center. Um, and for the simple bilayer graphenes, they have like similar properties to one layer of graphene, but the details of the properties might be different. For example, look at the graphs for the electron energy levels showing here. On the x-axis here is the K uh, wave number K, and y-axis is the energy level for the electrons. Uh, Ignore the blue curves for now, and focus on the red dot lines and green dash lines. You can see that at the near the zero energy level, uh, the red dotted curve, which is the single layer graphene, and the green dashed curve, which is a bilayer graphene, they have like a very close shape, but the bilayer graphene has a parabolic curve, while the single layer has straight curve, but it's kind of the same. Okay. Now the twisted bilayer graphene, the twist angle is very small for the twisted bilayer graphene. It's about 1.0 to 1.5 degrees, and the electronic properties of the material will change dramatically with such small angle. And both the single layer graphene and bilayer graphene has properties of semimetals, but the bilayer graphene, the twisted bilayer graphene here, it will act as a Mott insulator, or under certain conditions, it will transit to metal or superconductor. To understand what is happening with the slightly twisted bilayer graphene, we need to look into the Fermi energy here. The first equation here is the 1D Fermi energy. L is the parameter for which the area we're talking about for the electron, and N is the number of electrons in the system we're talking about. And similar to the 3D Fermi energy here, except we switched L into V, which is volume instead of length. Well, And also like Fermi energy here represent the uh, outermost electron that bond to a nuclear, the energy state of the outermost electrons that bond to a nuclear. And here is the third equation represents the Fermi velocity. It is like directly related to the Fermi energy. Well, um, or you can say it's like the electron speed of the electrons at the Fermi energy level. Fermi energy level here. So here, this graph, the x-axis shows the Fermi velocity of twisted bilayer graphene over Fermi velocity of single layer graphene. Y-axis, oh, actually switched. Y-axis shows the Fermi velocity of twisted bilayer graphene over Fermi velocity of single layer graphene, and x-axis shows the twisting angle. It is clear that there is a minimum point here between 1.45 degrees to and 1.5 degrees. This shows that like with slightly twisted bilayer graphene, there's a minimum Fermi velocity here, which means, well, the outermost electrons are simply like with zero velocity or near zero velocity. And the next concept we're going to talk about is the energy band. In this graph A shows energy of a free electron that can have the energy a free electron can have versus the wave number k. And graph B here shows the energy gap caused due to lattice structure and the Bragg reflection. The forbidden band, which is also known as the energy band, electron cannot enter into that band, which means the electron either be above that band or below that band. If the energy is not enough, the electron simply will, like for example, stay in the lower allowed band. If the energy is large enough added to the electron, it will hop into the second allowed band or the higher band. Next thing we're going to talk about is the energy gap of the slightly twisted bilayer graphene. The left graph here, it shows the delta energy here, delta E here shows the energy gap or the size of the energy band here. You can see that there's a zero energy band here between or not between, well, around 1.5 degrees, which is shown like more clearly here in the right hand side graph here. The blue curves that we ignored previously here, if you look at the center bar, the energy one here is energy zero axis, near energy zero axis here, you can see that there's a mixture of upper energy band and lower energy band. The upper energy band is the conductor or conduction band, and the lower one is the valence band. The mixture of them is showing that well, there's simply no difference between a conduction band and a valence band for slightly twisted bilayer graphene. The next property we're going to talk about twisted bilayer graphene is the Mott insulator. The Mott insulator is a kind of an insulator if we consider electron interaction in the lattice structure. It does not conduct any electricity at low temperature. it can also have like transition between insulator and metal, which means it can like simply transfer into a a metal or between a metal or an insulator if the like the uh, condition is right. Here, the inequality shows that like A here is uh, the lattice spacing, and AB here is a Bohr radius. AB, like that's for column interaction between electrons, and if A is larger than AB, this material becomes insulator. If A is smaller than AB, then it becomes a metal. Here is a graph that shows the interaction, like which changes the material from a metal into a insulator, the model insulator from a metal into insulator. The transfer between them, like a very simple explanation for that. If there's like an interaction you added into the material, there will be like a Fermi energy level created, and it previously one band will be separated into two bands, and one is the conductor band or conduction band, and one is the valence band, and the separation between them causes like the energy gap, and it becomes an insulator because like all the electrons are in the valence band, and there's no electron in the conduction band, which means there's no free electrons to conduct any electricity. And then we enter into the topic of magic angle, which refers to the small range of angles between 1.0 degrees to 1.5 degrees of the twisting angle of the bilayer graphene. The properties of that are the conduction and valence bands, they are mixing together, and they have like this material has interesting behaviors of electrons. The left graph here shows a device for bilayer graphene study. The purple and blue layers are the testing material. A bias potential is applied between the two layers to distinguish them in the potential field. The charge carrier density N is controlled via the metal gate below the testing material. Yellow cubes at the edges represents the probes for measuring currents and voltages through and across the material when carrier density is varying due to applied magnetic fields or variation of temperature. The right hand graph shows the results of this study. Resistance is shown with color difference in the diagram, with x-axis as the carrier density and y-axis as the temperature. Left one, which is labeled M1 here, is the testing material with twisted angle of 1.16 degrees, and the right one is labeled with M2. It has twisted angle of 1.05 degrees. It is clear that at low temperature here, twisted bilayer graphene can transfer from superconductor to model insulator or to metal as carrier density changes. The highest critical temperature for the left one is 0.5 K, and for the right one is 1.7 K. And for a conclusion, single layer graphene has high efficiency of electroconductivity and can be considered a good candidate for next generation of semiconductor devices. By tight binding two layers of graphene together and twist them with small angles, such material can have even better conductivity and could be considered a good superconductor. This is due to the change of lattice structure and therefore changing the electron energy environment. Further studies shows that twisted bilayer graphene can also reveal some important phenomena related to the Mott insulator and metal or superconductor transition. And that's all.